Very good morning, all. So, once again, let's resume with a new class. And last time we have talked of a binary search tree. You are well aware now. Primarily, the purpose is using it for effective searching. Well, BST was one thing through which we were able to search in order of log n time for most of the operations, including insertion and deletion. But the possibility of imbalance was one issue which we needed to address. So possibility of imbalance is one aspect where we can have one problem. Secondly, assume if there are, let's say, 10 raised to 6 records, each record of, let's say, 10 KB. If you use BST, of course, the height will be also quite more, height will be more, and the total BST will also be having a lot of data to be stored, and searching itself will take some time. So, and in real life, 10 raised to 6 records, etc. is not big issue. So in real life, effectively, you need a lot of big databases to be stored. Big databases to be stored. For example, let's say bank. Now in bank, it's not difficult to say that there are going to be 1 million accounts or 10 million accounts, and each account might have this. So in bank, your account number is a key, but along with account number, you have many other fields. So this collectively maybe each record to be of 10 KB approximately, and then maybe 10 raised to 6 account holders. And all this needs to be stored, and you go to a bank and search for an account number. So you need faster access, obviously, and you need all this data to be well efficient. Secondly, of course, permanent storage also needed, because when you talk of a bank, etc., all these things will be needed. So BST might not be the best choice. BST might not be the best solution, because imagine if it becomes imbalance. Imbalance will mean effectively you going into 10 raised to 6 approximately depth, and that you can't afford. Even if it is balanced, still we will have quite a good depth. So for situations like this, we use better data structures. Better data structures in the terms of new trees, which we call as a balanced trees. Yes, I'm talking of, as the word suggests, balanced. So we have a concept to start with a B tree. Later, we are going to talk of AVL trees. We are also going to see red-black trees and many more like that. So there will be a lot of ways to have all these effective searching and efficient storage, but all of them will ensure the balance. So the balance will be guaranteed and imbalance won't happen. And all these will also allow storage into the hard disk. Complete storage will be also there into the hard disk. So all these will be useful for the database storage and retrieval effectively. So database applications where you require good storage and the faster searching, you can use this. So as the word B tree suggests, balanced. Balanced mean effectively, in case of a B tree, the how balance is maintained is all leaves will be at the same level. At the same level, that ensures imbalance will never happen. So, but obviously earlier insertion and deletion you could do easily in BST without bothering about where is the leaf, where is the space available. You could reach to some higher depth, get a free pointer and store. So now this will be more tricky or more planning needed, so that balance doesn't disturb and still insertion deletion becomes possible. But searching will be quite efficient because a tree is balanced, so height will never be skewed, height will never go beyond a limit, and that is the advantage. Secondly, even to make it further more useful, each node will contain actually multiple records. Of course, each record has a unique key. For example, account number or any other. But now instead of one value, they will have multiple records in each node. Like in BST, what we stored was single record with a single key, of course. Single record oblique key. For example, I said I have here 20. So this node actually meant whole record. Okay, fine. So let me just once again have this. Stop this so that sometimes the screen sharing after recording enabled might not work well. So I'll just have this, and once again I will enable share screen. Yeah, so screen sharing is here, recording is in progress. I will resume from there. So I say that in this case, my BST has a single record with, say, key as a 20. Other fields also stored here, like maybe I'll say name, mobile number, address, etc., etc. Whatever. So all these are also stored. We focus on keys only because our whole searching, etc., insertion is only keys based. But actually, the record has all this data. So along with this 20, etc. Secondly, this side values are for the keys less than 20. This side we have values greater than 20. So in BST, single key automatically meant two children, one left child, one right child. In B tree, now this concept will be further extended. Multiple keys will be there. Multiple keys in sorted order, of course. So in general, there will be n keys, and hence there will be n plus 1 children. For example, just taking the example which book has already used, I will also draw that if I have this node, this has got m. Let's assume key is alphabet, P is a character. So M is a unique key. Along with M, other fields also stored here. And because there is, so this is the root of the B tree, there can be one or more than one value. For example, in this case, I say this, then there will be two children. M has two children, and first child is, let's say, values less than M. Similarly, this side values are greater than M. And let's say this side, I have some values QTX. Similarly, if it has two keys, there will be definitely three children pointers. So maybe I have a BC, Here I have F and G. This value is going to be JKL. For Q, accordingly, I have here NP. This side I have accordingly RS. Similarly for the T something, and similarly for the X also, let's assume YZ. And similarly values. Now, so when I say D, I mean the full record related to D, full record related to H, and similarly full record related to B, etc. So all these are leaves at the same level. Secondly, this pointer follows values less than M. So this pointer will follow values less than D. This pointer will obviously follow values or keys greater than D and less than H. So I can see here the values are F and G. This side, I will say, are nothing but values keys greater than H because it is on the right side, and obviously less than the previous field which has decided this value to be less than M. So greater than MH, but less than M because it is on the left child of M. So, or before child of M. So this is similarly, this side values are all going to be greater than M. So this side less than Q and obviously greater than M. This is in between Q to T. This is in between T to X, and this is obviously greater than X. So you can easily see this is how my B tree will be structured. You can easily see somebody has say root or someone has one key. So root will have minimum one key, but can have more also. All other nodes will have n keys. Of course, where there will be some limit, minimum and maximum limit on the n will be defined. So as per rules, there will be some minimum and maximum limit on n, and accordingly n keys are there, automatically meaning n plus 1 child or pointers. So each node will have a different number of keys. Somebody might have 2, somebody might have 3, and accordingly n plus 1 children. For example, here n equal to 3. So there are three keys in this node, automatically meaning there are 4 pointers. So if I talk of any node, something like a QTX, so I say it will have certain keys. First key, I will say key 1. This is key 2, and this is key 3. Similarly, I will say it will have a child 1 pointer, child 2 pointer, child 3 pointer, and child 4. So this is the way my total progress will be done for the binaries tree. Now, think of how will you declare your node structure. So you have to have a node structure so that while programming, you will be able to implement this. So I will say struct B tree, what it should have. First thing is, of course, how many keys it has. So I will store n. Of course, there will be minimum and upper limit, but because it's a variable, each node will have different number of keys. So n will be stored. Whether you say it as int, this is int is okay. And then now I have keys. So I will take a keys as an array. Now, in our case, it is a char, but sometimes it could be int, sometimes it could be float or whatever. For the time being, in our discussion, we are using char. So my keys will be stored. How many? we have to define an upper limit. So upper limit is actually 2t minus 1, where t is a property of B tree. So how t will be defined, we will see later. Assume that t can be, say, 2 or 3 or say 10. Minimum t has to be 2. So t will define how many maximum keys it can have. So it means maximum this. But instead of having this, I will actually store it as key 2t, because I'm storing from 1 onwards, and because there can be maximum 2t minus 1 keys, so I actually defined it 1 extra, because key 0 I am not using. For better simple programming, we are avoiding key 0, so it's a wastage, no doubt. For efficient programming, you can use it. Actually, you need a total 2t minus 1 keys, but because 0 is being avoided, I took it this. As soon as you have these many keys possible, child pointers. Child pointer means obviously star child. And what will be the data type? Star child as array. So array of pointers will be taken. And obviously, this will be struct B tree. Like in case of a tree, you say struct tree. In case of a BST, you say struct BST. Linked list, you say struct node. And how many child can be there? Maximum 2t children can be there. I am writing a +1 to this, so that the child can be from 1 up to child 2t. Maximum 2t minus 1 keys. So maximum total 2t children are possible. Let me just stop here so that my Zoom doesn't create a problem, and let me ensure that the recording is also being done. So let's resume. I just tried to ensure that the recording works well. So we said that we are going to have these many children to be stored, plus we will have extra field, which we call as a Boolean, to know whether we have reached to a leaf or not. Reason being, once we have reached to a leaf, then beyond leaf, no searching will be needed. So I will know whether it is a leaf or not. So for those nodes which are non-leaf, if I have to go to further children, the algo is still to continue, otherwise not. And if there are other fields to be stored of the records, other fields of all keys related, so all that data will also be stored here, but we are not bothered, not our focus, but you can easily see all that will also be stored. For example, for each key, the corresponding roll number, corresponding branch number, branch name, corresponding students, say if it is a college account, so I say corresponding mobile number, address, marks scored, JEE rank, whatever you want to score, all that will be as a part of this. So this is my total structure which I am going to use. Once I know this structure, obviously I have to primarily focus on 3 things: search, insert, and delete. So delete is, we are not going to do programming to implement, but we will discuss conceptually other things we are going to implement. So let's start with the search. Now search over source, whatever we have to pass, and then we have certain return type needed. So now search we will implement. Before I go for implementation, let's see that, say if I have some data, as we just discussed earlier, say I am talking of M, then we have got the corresponding B, C, F, G here. And corresponding, sorry, so after M I had, let's say DH. I'll take the same example which we have earlier used. So it will become easy, and the same example in the book also given. Then I have here Q, P, and X. This side I have a BC. Then I have FG. And then for H, I have, let's say, JKL. And similarly on the other side. Say I'm saying search for A. Obviously, I will start from here. One value only. So comparison with this, A is less than M. So means I have to go to the child one pointer. This is your first pointer. This is your second pointer. I will go this side. Again, I will compare with key 1 with this node A versus D. So I'm searching for A. A is less than D. It has to be means before D. Before D still will mean again I will be going to the next node or next child pointer. I will reach here. Again, I will first comparison itself A less than B will mean that effectively before B, and because there is leaf nodes, I will say A unsuccessful. So I will say A doesn't exist, not existing, unsuccessful. Say I'm now take an example, search for T. Search for T. I will start from here, single value. Obvious, I will go this side because T is supposed to be on this side. T is greater than M. No further children exist, no further keys existing. Guaranteedly, I go. Then I start from here. I will compare T versus Q. Q is bigger. So if T exists, it can exist on the right of T, Q. There are more keys available. So that I'll go right of Q. Right of Q, then I will reach to this key. T will be compared and found. I'm searching for, let's say, L. Search for K. Or let's say I'm searching for, let's say, G. I will start from here. Come to know that I'm supposed to go to this side because less than M means G will exist this side. Here I will do a sequential comparison. So within node, because there are few values, so I can just linear search can be done for the corresponding value to be compared. So I'm searching for G. G is greater than D. I don't know whether next pointer or even next. Then I go to H. H, I find that H is bigger than G. So if G has to exist, it has to exist under this pointer. So I will go to the child node. From here again, I will start searching. Comparison with F. On the right of F, G can exist. Go to this, I found G. Say if I was searching for something, let's say G2. So after G, say I will find that there is no more data. So G2 will not exist because we have reached to the leaf node. So this is what searching will be. So it is effectively nothing but extension of the search process which we have been using in BST. The only thing is in BST, what we did, key comparison, and then either go to left side, if not equal, if not found, based on the value, lesser value meant we went to left side, and greater value we meant right side. Now in B tree, things are simple. I will compare with all keys one by one in linear order, but need not go to the last. As soon as equality happens, I can guaranteedly correct or find this, or if key in node becomes greater the child pointer is known. Child pointer is found. I have to go towards that direction. So I need not go to the last. So this is what my searching in B tree will work. Go to that. And if it is leaf, of course, I can say unsuccessful. Leaf only will mean that, yes, it may not exist at all. If I have to implement this, now I can easily see, I will decide later what to have a return data type. Of course, you might think node star or something like this, but is that sufficient or not? We will see. Then I will say struct B tree will be passed. So I have struct B tree, let's say star current node, say root. In the book it is XU, so I'm using the same. And let's say I'm trying to search for some value K. In our case, we have used the data char, so I may have a K. Otherwise, the data type can be anything. So I'm searching for some value K. For example, K I said is, let's say G or A or Y or whatever I'm trying to search. So from X node, I have to start. Each node has a different number of keys. So I will require a sequential search. I will start from key 1 and go up to maximum keys, but in between I will stop. In between I can stop, so definitely I will need a while loop. Now while loop means I should have comparison with keys at most up to n, because beyond n keys don't exist. And what is n? I'll say not n exactly to be written like this. N is x arrow n, because x is the pointer. So n field, if I want to access, I will say I less than this and what. So I have to have some condition so that I can keep on incrementing I. So what comparison? Obviously, I will say x arrow key I to be compared versus K. So what symbol I have to use is the only thing I have to decide. When I have to stop this while loop, when I am able to conclude that I have found either the key or the child point. Before that, I should continue. So I can easily say that initially, like I am searching for, let's say I am in some node D and H, and I'm searching for, let's say, G. So first time I will compare G versus D. D is a lesser. So G has to be on the right, means I to be incremented. Currently I is 1. I needs to be incremented if key is greater. That means as long as key is lesser, I have to keep on incrementing I. As soon as, say, after this K will be incremented, I reached to H. H is greater than, so this false will happen. H is greater than G. Key is definitely G here, and this value I am comparing. So when H is greater, guaranteedly I have to probably go downwards, and the guaranteed direction is known. So I will stop. Now coming here, say I was searching for, let's say, H itself. H itself conversion will mean ultimately this will become equal. Equal will become come out of loop. Come out of loop. So come out of loop for equality, I can verify, and that means found. If I am able to find this, so I will say, of course, now I must check whether I have not crossed the limit. If I have not crossed the limit, only then equality will be possible. And when is the equality? When my K was equal to X arrow key. Let me just remove this word so that you can easily see now. So because I has not been incremented, if equality happened, I is the correct position. So I can easily see I was a 2, I is here, and I'm searching for H itself. So H is at key 2 itself. So if I have found, I can say definitely done, found, and found means I have to return something, means return something. Now what should be returned? Whenever we have a successful search, we should return the corresponding structure, corresponding full record with value k. What is that record? That record is within X, corresponding record is at index I. So effectively, I need to return two things. X, because X is the node which contained D and H. So this is my current X. I will require this whole structure to be used for some activity. For example, you want to check the balance of your account in the bank, or you want to add some amount, or you want to withdraw. This record will be needed now for further processing. This record is not as a separate node. So X is the overall node which my application will require. And within X, because I have already found where is my current record, then I will also be needed. So I have to return both. Now, if you write here node star, so node star will mean only X. If I say B tree star, so it will mean only I can return the X itself, but then I also to be returned. So you have to think ways and means to do this. For example, either you can have I returned as a call by reference, so that also you can do, or you can have a new structure created to be returned, new structure of B tree pointer and index as a collective structure created, and this can be returned, and then accordingly you can have return this. So it's your choice. How do you do? Second case, if equality didn't happen. So equality didn't happen means the search is still to continue. Search might continue if the leaf has not reached. But if I have reached to leaf, I can conclude that unsuccessful. So unsuccessful mean correspondingly return whatever you wanted to return, whether you wanted to return null or some special value or whatever. So if X arrow leaf equal to true, whether you write X arrow leaf or you write X arrow leaf equal to true, because it's a Boolean variable, one and the same thing. So it means done. If it is not a leaf, effectively now mean you have to search in a child. And which child? So obviously child is a something with relevant to I. Now obviously I will make a search call. Search call I'll make, but I'll just create a space in between. I will obviously make a search call here and search to whom? X arrow child. So think of what will be the pointer. Is it will be I, will it be I plus 1, it will be I minus 1, and k to be searched. And of course, child pointer has been found via above logic. Through this, I has been guaranteedly concluded, and I or I plus 1 or I minus 1 will be placed here and done. I intentionally left a space in between here because here I am going to write disk read the corresponding X arrow child. And why I am writing, it will be just clear after a few minutes. But this is an important step which I am writing intentionally, because this is an important step to be discussed. But before that, effectively my search process is over. Any doubts, any confusions, you can definitely ask, and recursively you can easily find that. Then we come to why we discussed disk read to be returned. Why I wrote that intentionally. So here is the reason that in case of B tree, the full B tree, as we said, is not in RAM, but full B tree will be stored in secondary memory. Say hard disk. Stored in secondary memory. Say hard disk. As we said, because it's very big also, in a RAM it may not fix. For example, I said 10 raised to 6 records, each record of 10 KB. So I might require more than that. Maybe if I say 10 raised to 10 records. So if I have total 10 raised to 10 records, each with the size of 10 KB or more than that. So total size could be, may not fit into RAM at all. Or RAM could be smaller than this. So may not fit in RAM. Normally, your databases are of terabytes. Databases are typically of size terabytes. Or many gigabytes, 100 gigabytes, or 200 gigabytes. If not terabytes, maybe if I say a normal computer, even if I say that fine, my computer has a 2 TB hard disk, but having a database of 200 GB, 400 GB is a common. RAM might not be that big. RAM, you could have 2 GB on some computer, maybe 8 GB on some computer, but this. So my total B tree is very big. I have these many records, these many sizes. So it means that selective nodes will be brought into RAM. Selective nodes of B tree will be brought into RAM. Because full tree can't exist as per requirement, as per need. For example, currently I am working on some node X. For example, X node needed. So X will be brought in RAM. Brought in RAM. Then I said X arrow child 5 needed. X arrow child 5 might not be in RAM. If not in RAM, bring in RAM. Say you needed X arrow child 5 for searching. If this is not in RAM, bring in RAM. From where? From hard disk. But bringing child 5 from reading hard disk, this is very slow process. Disk read is very slow. Because each disk read takes few milliseconds. Each disk read takes few milliseconds. But in RAM, maybe 1 lakh instructions can execute in few microseconds. So now imagine if you are able to make a good algo will be very fast to execute, fast execution possible because few microseconds will take for execution. But this whole algo advantage will be lost if disk read happens. If a disk read happens, read from, let me just write disk, happens. Because it will take, say, 30 milliseconds. Now, you executed a full algo in microseconds, say 40 microseconds, 30 microseconds, but suddenly you required 30 milliseconds. So for B tree, etc., target will be minimize disk access, minimize disk read or write. For searching, of course, we will not need a write, but reading will be needed. So now in searching, if a new child is to be used, we should remember that a new read might be needed. Hence, we must know that this is going to be the slowest operation. So we intentionally note down that unnecessarily don't put read. So read only if it is must. Of course, if it is must, it will make the things slow. But if it is needed, only then it should be read. So my aim will be optimize your algo or make sure every time that such that disk read or write is not unnecessarily done. Never done without necessity. Never done without necessity. That is what is the focus. So that's why I wrote disk read. In this case, it is must, but we remember that this will be making the things slow and algorithm will take few milliseconds. So we have to do. But now this search will take few milliseconds. Not microseconds. And if this search further leads to another search, if you further call it recursively, another child read after this also, that will further mean another read access, again slow. So we have to just remember this. Secondly, we said T is also decided accordingly. So how T is decided? T is also decided based on disk read capacity. I will choose in a way T will be taken such that each node size is closest and of course less or equal, never greater to disk reading bytes, disk reading capacity. What does that mean? It will be clear that in hard disk, everything is stored in terms of sectors. Minimum storage sector is 1 sector. Minimum storage is 1 sector or sector based. I will not say 1 sector because it could be more than this. So minimum storage is sector based. Even if you want to store 1 byte, at least full sector will be used. Sector means it is typically of 512 bytes. So maybe one disk read, let's say assumes reads, let's assume say 16 sectors. That will mean one disk read will be able to read 8 KB in a single read. Now, even if you require 1 byte, 8 KB will be read. Even if you require 100 bytes, 8 KB will be read. So aim will be make your node size just close to less than or equal to 8 KB. So that in each read, you are able to have the one full node read in a single disk read. Say your node is 8.2 KB. Now, this will require 2 read access. And that will make unnecessarily things slow. So your node has become 8.2 KB and then you needed 2 reads. In one read, you will get 8 KB. Second time, another 8 KB will be read, out of which your data will be only 0.2 KB needed, but you wasted one full extra read. On the other hand, if you wanted, say, 7.9 or just 8 KB node size, one read will be needed. So this is what, and one read lesser means very good performance. So now, how much should be T? That is how decided. Number of keys are T minus 2T minus 1. So if there are 2T minus 1 keys, means maximum there can be 2T minus 1 records, full records, plus 2T children pointer, plus you have N field, plus you have a leaf field. This whole size, so I will say this whole should become less than equal to 8 KB. Choose B such that. Choose T in this way. Because I said 8 KB will be reading capacity. I assumed read capacity as 8 KB, disk read capacity. So I will say choose your T such that you are able to have node size according to this. That less than equal to 8 KB you are able to reach. Of course, we will aim to have more or bigger KB, bigger T will be always useful. Why? Bigger T will mean more keys in each node, means effectively lesser depth will happen, or the total height of the tree will be lesser, and of course I will be able to do better. For example, if I say T equal to 5, and if I wanted a 10 raised to 6 records, I will get some height h1. On the other hand, if I can accommodate T as a 10 and I require 10 raised to 6 records, h will be less. h2 will be less than h1. Because T equal to 10 means I will have maximum 20 minus 1, 19 keys possible. At the same time, T will make a minimum keys boundary also. If a T is kept as any value, minimum keys will be T minus 1 and maximum keys will be 2T minus 1. So balance will be ensured by having a minimum keys also and maximum keys also. Yes, this root can have one key because root can have one key, but others will have minimum keys. Because initially root might have less than also one or more keys, but other nodes must have minimum keys, must have at least T minus 1 keys and at most 2T minus 1 keys. Accordingly, the children, etc. So this is how my B tree will be decided. So if I have, let's say, T equal to 2 taken, T equal to 2 will mean minimum, let's take T as a 3 so that things become easier to discuss. So minimum 2 keys in each node, and so each node except root, of course, minimum 2 keys, and each node will have maximum 5 keys. 5 keys automatically mean maximum 6 children. And this automatically means minimum 3 children. 2 keys mean 3 children. 5 keys mean 6 children. So if a t equal to 4, I will say minimum 3 keys, maximum 7 keys. You can easily see more keys will mean the size of the node will increase, bigger size of the node will increase, width of the tree will be more because I will be having more keys in the single node. Width increases, height decreases. And of course, accordingly, we can have the max also. So minimum this, maximum this. And accordingly, children also. Complexity of search algorithm. You can easily see one while loop, maximum how many times it will execute, 2t minus 1 plus 1 to terminate that. So I can say effectively 2t times. Depth-wise, recursion is there. So recursion will mean maximum height times of the tree. So I can easily say if height is h, my total time complexity is going to be 2t into h. Every time the same thing happening in worst case effectively means order of t into h. What will be the height? Of course, depending on the t, accordingly height you can mathematically calculate. And of course, it will be something log based, but not log based 2. So you can think of that and accordingly this will be done. Just to stop here, I'll quickly show you a sample code of searching and implementation so that you can practice. Those who are not so good in programming, they can easily see this code. So for example, here I can define my t. Say you can define a t as a 2 or 3, whatever you require as a constant. Then your b tree, number of keys, array of keys. And because I'm storing it as a 1 to 2t minus 1, that is why I have taken it an extra. Child pointers, 2t plus 1 taken so that we can have extra and a leaf stored. Search, effectively, I have to do I starting. Here, I will be going for this comparison and I plus plus. If I have reached to something, maybe either I can this or return in any other way. So if this I have taken as a call by reference return or return in any other way. Return x plus and I in sum. If x is leaf, then whatever to be returned, else I have read, discrete, and then search to be called. And this index I am returning call by return. So I am passing it from here as a call by reference. That's it. I'm not going to go into more detail, but let me stop this. And it was just to show you some of the sample codes. With this, let me stop here. Next class, we are going to have insertion to be done. So please revise and if possible, read from the book some idea about the insertion, and we are going to implement and understand the insertion logic in the coming class. Bye-bye. All the best to all of you. Let me stop recording.